All right, let's dive into one of the most common questions in science. One that billions of us experience every single year, but very, very few can actually get right. How do airplanes really fly?
Really stop and think about it for a second. How on earth does this massive 400-ton metal tube, just packed with people and luggage, get off the ground and just hang out at 35,000 feet? Well, the answer you probably learned in school sounds pretty good, it's intuitive, and it's almost completely wrong.
You know this one, right? The equal transit time theory? The idea is that air particles split at the front of the wing, and they just have to have a little reunion at the back edge. And since the top path is longer, the air on top has to book it, has to go way faster to get there on time. Faster air, lower pressure, and boom, lift. It's a really nice, tidy story.
Yeah, except that story isn't true at all. This explanation, the one you'll find in countless textbooks and websites, is just fundamentally flawed. And look, this isn't some new revelation. Aerodynamicists have known this for a long, long time. Here's the fatal flaw in that whole theory. There is no rule, no law of physics anywhere that says air particles have to meet up again. It's just not a thing. In the real world, the air going over the top moves so much faster that it gets to the back edge way, way before the air from the bottom. That little reunion party, it never happens.
So if the most popular explanation for flight is basically a fairy tale, what's actually going on? Well, to get to the truth, we've got to clear away a little more of the fog that surrounds this whole topic.
And that longer path theory isn't the only myth out there. There's also this skipping stone idea. This one says a wing works just by deflecting air downwards off its bottom surface, like when you skip a stone on a lake. And while that's kind of part of it, it completely ignores the most important part of the wing, the upper surface. The reality is you need both surfaces working together to turn the air.
All this confusion has led to this huge, decades-long argument that's just made everything way more complicated than it needs to be. It's usually set up like a big title fight between two heavyweights of physics, Bernoulli versus Newton.
So in one corner, you've got Team Bernoulli. They say lift is all about pressure. You get low pressure on top of the wing, high pressure on the bottom, and that difference in pressure literally sucks and pushes the wing up into the air. Then in the other corner, you have Team Newton. They say, no, it's just simple action-reaction. The wing pushes air down. Newton's third law says the air has to push the wing up. End of story.
So, which team wins? Is it all about pressure, or is it all about force? Who's right?
And the answer is, plot twist, they're both right. This was never a real debate. They are just two different ways of describing the exact same thing. As NASA likes to put it, arguing about this is like arguing if a car moves because of the engine or because the wheels are turning. The two are completely connected.
Think about it. What is a pressure difference, really? It's just a force spread out over an area. So that pressure difference is the reaction force. Team Bernoulli and Team Newton aren't fighting, they're sitting at the same table, just describing the meal with different words.
Okay, now that we've settled that fake debate, let's focus on what the wing is actually physically doing. What is the one fundamental thing that's happening to create lift?
At its absolute core, it's this simple. A wing flies because it forces a truly massive amount of air downwards. That's it. That downward shove on the air creates an upward reaction force on the wing, and we call that force lift. So the whole job of a wing is just to be a super efficient air deflecting machine.
But you might be thinking, how can air, which is so thin, create such a huge force? Well, try this analogy. If you jump into a swimming pool, the water moves out of your way pretty easily. But if you were to jump from a kilometer up, hitting that same water would feel like smacking into solid concrete. Why? Because you're moving so fast, the water molecules literally don't have time to get out of the way, so they push back, hard. For a plane screaming through the sky, the air acts just like that water.
Okay, so we've got it. The wing pushes air down. But this brings up the most important question of all. It's pretty easy to picture how the bottom of the wing deflects air down, right? But what about the air going over the top? Why does it so perfectly follow that downward curve? Why doesn't it just fly off in a straight line and leave a big empty space behind it? The answer to this is the real key to understanding lift. The answer lies in a beautiful little principle that you don't hear about much in school, but it's everything in aerodynamics. It's called the Coulomb condition. The Coulomb condition basically says that when air flows off a sharp edge, it has to do it smoothly.
Nature just hates the idea of air trying to whip around that razor-sharp trailing edge at like infinite speed. It's a physical impossibility. So to avoid that mess, the airflow from the top and the bottom have to meet up perfectly and flow off that edge together.
So how does the air figure out how to do this? Well, right as the wing starts to move, for just a split second, the air tries to do that impossible whip around. This creates a little swirl, a starting vortex, that gets kicked off the back of the wing and it's just left behind in the air. But because of the conservation of momentum, as that vortex is left behind, an equal and opposite circulation forms around the wing itself, almost like a ghostly whirlpool that's now bound to it.
And this is the secret sauce. This bound vortex, this circulation, is the magic ingredient. It adds to the speed of the air flowing over the top of the wing and subtracts from the speed on the bottom. It's this circulation that gives the air on top that extra superspeed, forcing it to hug the wing's surface and leave that sharp edge smoothly, perfectly satisfying the cutter condition.
So let's put this whole puzzle together. It all starts with the wing's sharp trailing edge, which enforces the cutter condition. To satisfy that condition, a circulation of air is created around the wing. This circulation then accelerates the flow over the top, which turns a huge amount of air downwards. That's your Newtonian force. All that downward moving air, in turn, creates a big pressure difference between the top and the bottom, and that's your Bernoulli effect. And the final result of all these things working together is lift.
What's so amazing is that none of this is actually new. Scientists and engineers have had this figured out for more than 100 years. That great debate between Newton and Bernoulli, it's not a real debate among people who actually design planes. It's just an argument between two different, overly simple stories we tell in school, when the real story is just a bit more complex, but way more beautiful.
And that really leaves you with a final fascinating thought. We have mastered flight. We've built an entire global civilization around this technology, and yet the most basic explanation for it is still completely misunderstood by most people. It kind of makes you wonder, doesn't it? What other simple things that we see every day are we getting totally wrong?